Train? Okay, you're third. All right. Okay, so there's a couple sheets being passed around. If you're coming in late, you should have one that says peer review and one that's in-class writing. So if you don't see those, if you have a pile in front of you, over there, could you pass them over to folks who need them? Raise your hands if you don't have a sheet. Thank you. So today we're going to start diving into a little bit more detail about what life is on Earth. But before we begin, I want to do a few quick announcements. Anyone catch the lunar eclipse this weekend that I forgot to tell you all about? You caught it? What do you think?
I liked it. Wasn't there like remnants of it yesterday? The moon was yellow. I saw the other moon.
So unfortunately, when the moon's yellow, it means we have crap in the atmosphere.
Oh.
Which is a completely different effect. But no, the lunar eclipse happens over a relatively short period of time. Was it completely? What color did the moon actually turn? Do you remember?
I just remember like seeing it and passing, but I was busy, so I just looked up. I was like, oh, it looks like an eclipse. And I looked around.
It was like really early in the morning too, right? You're busy. Okay. So if you missed it, because I missed it because I didn't even know about it. That's what happens. Astronomers don't always know what's happening in the sky. Have no fear, because these things tend to happen in tetrads, 4 at a time. And our 4th tetrad is coming up in September. So if you're around September anywhere in North America or Europe, which is a good swath of the world, you should be able to catch that one as well. I want to introduce our TA, Kurt Thompson, who's actually here today. Hi, Kurt. Kurt's going to be helping out with several aspects of the class, including problem sessions, which we'll talk about in just a moment, and some of the labs that we'll be starting this week. He's also going to have office hours. I haven't told Kurt about any of his responsibilities yet, but he's also going to have office hours. And Kurt, do you have a particular date or time that works for you?
I didn't set it exactly, but I think Tuesdays. So we talked about.
So Tuesdays, like
about midday, I think 11 or 12, but I'm not exactly sure.
Tuesdays, 11 or 12. Okay, I'll write that down. All right, so I'll make sure that that's on the website. A very fancy writing paper here. Tonight we're supposed to be showing for the night lab. The weather looks terrible for tonight. This is unfortunately a feature of doing any kind of things that involve stars, is that sometimes our own atmosphere gets in the way of them. And so I'm going to do a quick vote here. The weather should pass by the end of tonight, so I'm expecting that either tomorrow or Thursday night is clear. Who would like Wednesday? Who would like Thursday? Thursday it is. Okay, so we'll be doing Thursday for the night lab, and that'll be 8 to 10 p.m. Now you don't have to be. Oh, and it's going to be out here in the quad area, just outside the building. We don't have a lot of dark spaces on campus, and that's not a particularly dark space. But I'm going to see if I can get them to turn off the lights for at least for a couple hours out there. But it's just out there. The lab itself should only take you about an hour. I'm only having it from 8 to 10 to sort of accommodate time for people to get in here. But please try to show up by 9 o'clock at the latest, because you will need an hour to finish the lab. Homework number 1 is now online. Yes, ma'am.
Do we need to bring anything for the lab?
Bring a pen. You might want to bring a calculator. I don't actually think we have any heavy calculations in the lab. It's mostly kind of observing the sky, figuring out directions, making some very coarse measurements of angles and stuff like that. But bring a pen. That's probably the best thing. You'll have a worksheet for it. Any other questions about the night lab? Okay. Homework 1 is now online. That's due on Friday. I will have office hours starting this week on Thursdays at 12. My office is just around the corner over here in Surf 340. You probably walk past it to get to the class here. So I'll be there at noon on Thursday. And so a couple of you raised my attention that we actually have a problem session scheduled. I didn't actually even know this. So my question, this is going to be completely optional, so because I wasn't actually planning on doing this. But we do have homework assignments, and I do want to provide an opportunity for you to get help on those assignments as they come up. And so we'll keep the same schedule as scheduled in the book, which is Wednesday, 7 to 8:30. But how many of you think that at some point in the quarter you will actually want to go to problem session? That's enough. Okay, so Kurt, put it in your book.
Okay.
Okay. So we'll have the first one tomorrow, and that will be based on homework number 1. And Kurt, I'll make sure I get you the problem solutions. Yes.
And we're also still having discussion now.
Okay, yeah. So discussions. Did you send me an email asking me like a list of questions? Yeah. So by the way, anytime you have questions about the class, please post them on the discussion board because you're probably not the only one that was completely confused by the schedule right now. So just a reminder that the discussion section is kind of our third meeting hour, and it's meant to be doing sort of some lab activities, but on occasion lab activities can't be done in that meeting hour. For example, observing stars. Not very good at sort of 4 o'clock in the afternoon. So when we have a lab that's scheduled on off time, there's no discussion. So there's no discussion tomorrow at 4 o'clock because we're doing the night lab, right? Now, there will be, and I think even starting next week, we're going to be occasionally doing labs that do require to be done during the day. And in fact, the scheduled class time is kind of the best time to do them. And so in those cases, I will have the lab during the lecture period. And then during the lab, we'll have a shortened sort of lecture for that course, okay? So you should, if you can, make sure to block off that time, but keep in mind that we may not actually use it in every week because we may be doing things in different hours. Okay? We'll probably use it most of the weeks, but particularly this week we will.
So tomorrow's there's no discussion.
So tomorrow there's no discussion because we have a night lab on Thursday. Okay. Any other questions on the schedule? I know it's a little bit in flux, and I'm trying to make sure that the Google Calendar is as up to date as possible, but I think I haven't actually put in all the discussion sections yet. Okay. Any other questions about the class in general? Yes, sir.
For homework 1, do we have to print out the pages online?
You should because the last two. Okay, this is actually a question. The last 2 or 3 pages are things that you'll be filling in the assignments on there. If you would prefer to just write those off on your own on a Word document or something like that, that's fine. But those end parts should be in my box. So I will have a box outside my office on Friday at 4. That's when the deadline for homework is. I actually want the hard copies. It's the easiest way to grade them. That's for the written problems on the back end of the homework. The first assignment, which is the bulk of the homework, which is this sort of community poll about attitudes about alien life and stuff like that, that you should be actually turning in online, and there's an online sort of assignment where you can actually post that. And in addition to sort of just the 1-page write-up, and someone asked about like words versus pages, so make it readable, but just a page. Like this doesn't have to be like a treatise on your community attitudes of aliens. It should just be kind of a summary of your methodology and your findings.
So
yeah,
double space or just single space? Like just making sure.
So double space is a little easier to read,
Okay.
but don't make it like 20-point font double space where you have like 5 words.
Yeah.
Try to fit a few hundred words on a page. So if that works out to be space and a half, I mean, usually words default as 1.2 lines or something like that. That's very readable.
Okay.
But like single space 9-point font is not readable.
Okay.
Right. So just use some, you've written papers before, so use some judgment in sort of what's readable. So that write-up and any data you have should be uploaded to the website. Okay. Is any questions on that? This is a little bit different format than we have for some of the other homeworks.
So
Yes,
we're
ma'am.
submitting the writing assignment online. Do you also want a hard copy of that in your box by 4? So you want a hard copy of the paper and the online submission?
Yeah, I kind of would. It's easier to read. So thank you. I will make sure this is clearly noted on the webpage, but if you could provide a written copy of the writing assignment in addition to the one you uploaded on TED, that would be helpful. So I will make sure that it's noted in the answers. But the data I also want to make sure we see, because it's actually the data is the fun part. Any other questions? Okay. All right. So today we're going to be doing our first news report sequence. We've got three of you giving news reports. You should have in front of you, if you don't have 2 pieces of paper, there's some floating around. One is titled Peer Review Notes. And I just realized, actually, I really need like 3 of these for each person. So how many extra do we have right now of the peer review notes? Okay. So Okay, so 'cause we're just trying to throw time. What I'd like you to do is actually take that peer review notes paper and fold it in best as thirds as you can, and then tear that into 3 pieces of paper, because we need to actually get 3 different sets of comments. And just write your name and the name of the speaker as they come up. The idea of this is not something I'm collecting or grading in any way, but this is a way for each of you to give some feedback to each other on their presentations. Now remember that the final project is a presentation, part of that final project is a presentation. So this is the opportunity to get a little bit of feedback about what really works for your presentation and what you might think about for the next time. Now, these are short presentations, you're only doing for a minute, so don't get too stressed out. But just comment on what you see, both in terms of the slide and in terms of the sort of presentation of the material, right? This is pre-practice for the final project. Any questions on that? All right, so Ivana, you're looking around. You want to do it from there?
That's okay.
Okay, come on up.
Okay, so recently there have been indications that there may be hydrothermal activity on Enceladus, which is one of the moons of Saturn. It has a very icy, thick outer crust. And it caught the attention in particular of scientists in about 2005 when the Cassini-Huygens spacecraft did a flyby of the moon and noticed that there were geysers erupting from the southern polar region of the moon. So then further investigations revealed, based on gravitational measurements, that there's likely a subsurface ocean in that southern polar region. And so the Cassini-Huygens spacecraft has been investigating, the surroundings of Saturn, and it has recently also detected nanometer-sized silicon dioxide, also known as silicon particles, in Saturn's E-ring. And the E-ring is the second outermost ring of Saturn. It is also the ring in which Enceladus is located. So what is unusual about these rings is that they're very different compared to much of the other particles that compose Saturn's rings. They tend to be dominated by water ice particles. So scientists have been wondering what are the origin of these particles. And based on computational simulations as well as lab experiments, they've determined that these have very unique formation conditions, and that they require temperatures of about 194 degrees Fahrenheit and need to be made in water with relatively low salinity, and that is has a pH above 7. So in kind of alkaline hydrothermal conditions. So I think it's fairly obvious this can't be made in the immediate surroundings of Saturn. So Enceladus is a good candidate for where this could be made. It could be made in hydrothermal vent kind of environments, much like in Earth, silicon dioxide is made in hydrothermal vents. And so if this would be possible if Enceladus had a warm core that was heated by tidal heating, that is the gravitational pull of Saturn. So, and this is very important because if Enceladus has hydrothermal vents, that is an indication that it is a possibility that hosts life. Because on Earth, hydrothermal vents are hotspots of biological productivity, and and they're pretty good at supporting life. Oh, and they're not dependent on direct solar input, which is very important for an icy planet like Enceladus, which is very far from the sun. So this would have far-reaching implications for just life in the universe as a whole, because gas giants with little tiny icy moons are very common configurations in the universe.
Okay, thank you, Anna. While you're writing any comments, does anybody have any questions? Take them from there. Before she sits down. I have a question. So, you say this is unique formation conditions for silica. So that's the material that's in the ring?
Yeah, and the ring that Enceladus is also in. So it's likely being ejected by the geysers.
Okay. Are there any other possible sources for the material at all that are discussed in the?
not in the news article. I also looked at the primary source of the Nature article. So it's just, I think the main point was that just the temperatures are so high and it needs to form, I think, in water.
Mhm.
It's formed by the water interacting with the material in the core and then becoming super saturated with the the mineral and then being ejected. And also the fact, I think, that they're nanometer sized
Mhm.
is also influences kind of what they decided is the best formation process.
Okay. Okay, next, Izzy.
So hi, my name is Izzy, and so I'll be talking to you about the galactic telescope or gravitational lens and galactic telescope. So recently, scientists using the Hubble telescope have been able to see this image, which is the same supernova multiplied again and again. And this would actually not be able to see even with the Hubble telescope without help from the universe. So this supernova actually, or this star exploded actually 9 billion years ago. So this would normally produce an image too faint to be seen, even with the telescope, like I said. And like it is seen, it has been seen multiple times throughout like history. And timing the delays between its reappearance will help us further understand dark matter and how fast the universe itself is expanding. And so the reason this can be seen is because, it relates to Einstein's theory of relativity, which recently celebrated like a century of being discovered. So he proposed that matter and energy warp time and space similar to the way a heavy body sags a mattress. And in this case, like we learned when we did that something in class, or a finger thing, light bends around massive objects, so it distorts like the image. And the way the stars align, creates a different effect. Like this image right here is called an Einstein cross, so it's the same image 4 times. And this right here is a halo, and that's because like the object in question was directly behind the galaxy or whichever lens we're using to look at it. And in this case, a cluster of galaxies bended the light around the supernova so that it produced multiple images. And actually, each image represents a different time in the supernova. So scientists are thinking that like it's not a multiple image of the supernova, but it's the same supernova going in slow motion. So scientists are looking at it over and over again to like further understand dark matter, like I said. And the star itself actually is pretty unique because it's getting brighter over the past few months, which normally wouldn't happen. It would die out by now. And it's producing a light spectrum that has never been seen before by any supernova. So, yeah.
Any questions?
So what we're seeing is basically the light taking, like it goes different ways around the lens.
Yeah, so like,
And then it takes different times to get here.
yeah,
Okay.
so like over there it takes like 6 months or something, I think I read. And then over here it's 2. Yeah, it's pretty mind-blowing.
Yeah, seriously.
It took me a while to,
Yeah, I'll say, like these things, Izzy's right, that this is one source, one star, one galaxy that's just taking different paths. In this case, it's almost like a kaleidoscope. If you ever use like a kaleidoscope thing where you turn around, you get multiple images. That's kind of like this galaxy cluster is acting like this kind of lens that makes multiple images. But this is really cool because it's not just changing in different places, but it's actually taking different amounts of time to get there. So that's pretty cool. Any other questions? I'll make one point. You said that when we did the finger thing, that light was bending around our finger. It's actually not. We don't have enough gravity in our finger to actually
I'm
bend the
just
light.
like saying that it changes the picture.
Okay.
So, yeah.
Okay. So it changes the direction that light's coming from.
Yeah.
Yeah. I'll agree with that. Yeah. Okay. Okay. All right. Thank you, Izzy. Okay. Okay. And again, remember, please provide constructive feedback for these presentations.
Hi guys, my name is Trang, T-R-A-N-G, and the article I chose was a calculation that predicts hundreds of billions of Earthlike planets by George Dvorsky, and he wrote this article towards the beginning of this year. And basically the article is about this band of Australian astronomers who came together and used a centuries-old technique called Tzeentch bode relation. and they found that many stars in the Milky Way was a host to at least 1 or 2 terrestrial planets that could foster life. And so what is this Titius-Bode relation? Well, I'm going to take it straight from the article since it's really straightforward and simple. It's basically, it hypothesizes the celestial bodies that space-based and terrestrial telescopes cannot detect. And so Johann Daniel Titius discovered this in 1766. And he said that the planets use an arithmetic rule when orbiting in a solar system. And in that table, you can see that there's the law and there's the semi-major axis. And if you guys can see at the top, that's the formulation that they use. It's pretty basic, pretty simple, which I thought was pretty cool. So just to let you guys know, this is just a prediction, you know, the numbers aren't definite. Of course, we would need like concrete proof. And I think that that's pretty cool, the mystery of it all. So I was never drawn to sciences or mathematics, but you know, the article made me scroll through and read really quick. It was really interesting that just a simple calculation like that could find life. And in the article, it also said that if there is life, that's awesome. If there isn't, then there isn't. But since we haven't found life yet, you know, we know that the solar system isn't teeming with alien life. So yeah, I found this fascinating. So I hope you guys did as well.
Okay, any questions?
So it's just an equation to find or predict percentage of life.
Yeah, the astronomer said that the calculation isn't perfect, of course. You know, there are lots of factors that play into this, but that's just like a simplified version. Yeah.
Can you explain how they go from this to then saying that there's hundreds of billions of planets? Like, what did they actually do with this equation?
They measure like the semi-major axis. I'm not sure, they didn't go into depth, but they in the article they have graphs and all the numbers that they found, and they like located which location and which moons and planets were closest and stuff like that. Yeah, I wasn't too sure.
Any other questions? Okay, thank you, Trent. Okay, so all three of those were excellent models of the kind of news reports that I want to see. It's a good sort of summary of what the report is on. And notice I was probing in some cases kind of what's specifically relevant to sort of astrobiology. Most of you actually touched on that in some degree, so that was good. But that's kind of, we want to make sure we make connection back to the class, because all of these topics that you just presented, you know, finding other planets, you know, what are the elements of life, you know, where are they coming from? Supernova are going to be actually factored into the talk today. So these are all going to have pieces in sort of our astrobiology course, and so it's good to have sort of these other perspectives. Okay, all right, let's move on. So today we're going to be talking about, as I mentioned, a little bit more into the physical sort of underpinnings of our sort of search for life in the universe. And so this week is going to be a little bit heavy in physics, but this is kind of just a very summary kind of course of physics that we're going to be talking about that's specifically relevant for life in the universe. So don't freak out too much. It's not 10 weeks of physics hidden in front of you. So today we're going to be focusing on three pretty big topics in just an hour: matter, energy, and forces. These are the kind of things that we're going to cover. We're going to talk about sort of this hierarchy of matter in the universe, because across this entire hierarchy, from the very smallest quarks all the way up to sort of the most complex substances, is all fair game for sort of understanding what gives rise to life, what is life actually made of, and how we can predict what life will actually be in other planets if it exists. We'll tie this to different fundamental forces and energy scales, and then sort of understand a little bit how what the actual origin of the elements are that make up life, and how that emerges directly from the fundamental forces of nature. All right, so just to kind of cover our definitions, because if we're talking about matter and energy forces, we should talk a little bit about what those actually mean. Newton was actually one of the people who kind of first gave us a at least working definition of what matter is. This actually comes from his book called Principia, which if you took the Physics 1A class was mostly what Physics 1A was all about, was that one book. But he describes what matter is so it says the quantity of matter is that which arises conjointly from density and magnitude. He goes into some relation between here, and he does it by body or mass. This is a terrible explanation. All right, it doesn't really tell you anything. All right, what it really tells you is that there's something called mass, or there's something called matter, and that's just taking density and multiplying by volume. But then you got to ask, well, I can understand volume because it's kind of the size of something. What's density? Well, density by definition is mass divided by volume. It's a little tautological, right? In Newton's time, no one really understood what matter was. It was just stuff. It was substance. You could point to it, you could hold it, but to actually describe what it is at a fundamental level was in the 17th century beyond the science of that time. At that time is sort of the science of having absolutely no tools whatsoever. You can hold things, you can manipulate them, you can bake them, you can cook them, you can set them on fire. But actually getting down to the very core elements of what matter is will take a couple centuries from this point. That's even more easy to understand than this concept of energy, which is a concept that underlines a lot of physics and actually a lot of all the sciences. Understanding what the amount of energy is in a system, how the energy flows between systems, and what characteristic the energy has can provide a lot of insight into how different systems work. So I'm going to be as vague as Newton and just say that energy is a quantity that describes the amount or potential for motion, action, or work, which again is very vague, and partly because energy itself is kind of a theoretical concept. We can't actually hold energy. We can't point to it. We can't put it in a bowl and measure it in a very, sort of physical science kind of way. It's more of a quantity that we use to describe these properties of action, motion, and work. And it comes in many different forms depending on what kind of system that's involved in. So, kinetic energy is the action of motion, right? Me actually moving around is kinetic energy, right? I'm expending some kind of energy so I can move my arms back and forth and walk your leg. This is motion, so that kinetic energy covers that. But there's also energy associated with fundamental forces like gravity, right? The fact that I'm holding this clicker, I better not drop that one, drop this one, holding these keys up in the Earth's gravitational field means that these set of keys actually have some amount of gravitational energy. And when I release them, I'm actually transferring some of that gravitational potential energy into the motion energy, kinetic energy of the keys, which once it hits the ground makes a sound energy, right, which is pressure energy in the air, right? There's all these sort of transfers of energy going on. And probably the most interesting, of course, is that even mass itself has an energy associated with it. And that's one of the predictions of Einstein, sort of what was talked a little bit about in terms of the supernova. So energy is able to transfer between these different forms, and a lot of the processes that we'll talk about in astrobiology, not just in terms of life, but also how elements get formed, how planets are formed, stuff like that, are based on the sort of transfer of energy, how energy is transferred through systems. But the important thing to keep in mind is that when we talk about an entire system, a closed system, that total energy is conserved, and that allows us to sort of make some calculations about how much energy is available to do things like build plants or build planets. So here's just one of the models, and you had a question on this on your pre-lecture quiz, how you go from different forms of energy, for example, to power wind turbines. Well, the wind turbines are actually powered from wind. The wind is generated from the energy that the Earth receives from the sun, and the sun is actually creating energy in the first place by converting mass directly into energy. We'll talk about that process a little bit later, right? But there's all these different chains in nature on this transfer flow of energy, and that's one of the ways that we can sort of track how things and systems work. All right, and the third of these sort of concepts are forces, and I like to think of forces as just any way that things interact with each other. All right, we talk a lot about, for example, in basic physics, about forces like contact forces, the friction on this table, the normal force with which I hold this pen up in the air. Right? These are all interactions. I'm actually physically touching this object. I'm actually having a touch between the table and this marker in order for those friction forces to occur. So a lot of the forces in nature that we think about are forces that occur when two things are in contact with each other. But in fact, they're all based on the four fundamental forces of nature: gravity, electromagnetic, strong, and weak. These two you've probably had some experience with, right? We're living on a planet that has mass. We have mass, and so we're naturally bound by gravity to the Earth, which is good, because otherwise we'd float around in space, and that would suck. But that's a natural force in the universe where all mass attracts all other mass. This is one of the things about fundamental forces. There's some property of a material, and there's some way that those properties interact. So for gravity, the property is mass, having this mysterious substance. And just having that allows a force to emerge where we're attracted to other masses. In most of the cases, we're attracted to the Earth because Earth is pretty massive, but there are gravitational forces between all of us right now. Very weak ones. Electromagnetic, the property is charge, positive and negative charges, and we'll get to those a little bit. But that's the electro. We also have magnetic, and that's positive and negative magnetic poles, which are north poles and south poles. So if you ever play with magnets, of course, you've got these two places. And we have this property for electromagnetic forces that like repels like and dislike attracts each other. Right? This is just a property of that force. Fundamental force. It's just the way the universe works. Right? We don't have any a priori reason why this force should exist. It's just one of the properties of nature. These two are going to come into play when we talk a little about the structure of matter. But this is a really important one because without this force, we wouldn't have any elements other than hydrogen. Right? This is the force that binds the nucleon inside an atom together. Really important force. Right? And this one is probably the least sort of well known widely, but this is also involved in sort of the scale of nuclear physics, the properties of atoms. It leads to a lot of decay properties. And it will be something that we touch on when we talk about radioactive decay. But all these forces are, again, fundamental nature. They're a property of our particular universe. And again, there's no reason why they have to be like this. We could not have a weak force. And that would actually have really terrible consequences on whether we'd have life in the universe. So the fact that we have these forces is, in sort of what's called an anthropocentric point of view, the point of view that we have to have these forces in order to have life. Again, a little tautological, but this is what they are. This is what we have in our universe. So how do they play? How do all these things play together? Well, to start this, I'm going to do a little bit of a writing experiment. So your other sheet of paper should be your writing assignment. And wrong thing. I want you to take 2 minutes and consider the paper you're just about to write on, and write down 10 characteristics of it. Any characteristics. 10 characteristics of the paper you're about to write on. Now, if you're at like 4 or 5 and you're starting to get stuck, you can play with the paper a little bit. Feel how it moves. Test it a little bit. Does it tear? How easily does it tear? Can you see through it? How heavy is it? What does it smell like? Everyone does it. Who needs more time? Okay, 10 more seconds. Not much. Okay, second part. Oops. I want you to tear off a small piece of this paper. Just tear off the corner. And keep tearing it any way you can until you have absolutely the smallest unit of paper you can possibly make. If you're finding that you can't tear it with your fingers anymore, maybe you can use your pen, or you've got a ruler or something like that. But try to get this to the smallest, tiniest piece of shred of paper you possibly can make. You can use tools. We are human beings. All right, once you've got that down as small as you can, I want you to answer this question. Is this still paper? Which of the 10 characteristics you wrote down, or up to 10, does this thing still have in your hand? Take 90 seconds to write that down. Okay, I'll take 3 reflections. 1. 2 more. 2, 3, please.
I said it's still paper. It's made of, the only thing that's changed from this paper is the size and the shape.
Okay.
It still had all like probably light and like structure, foldable.
Okay. Okay. Please.
I also said that it was still paper because from the on, I just wanted the shape because it was right.
Okay.
I still said it was paper. It's still white, smooth. Like it's not smooth anymore, but it's still made of tree. You can still burn it. It's not transparent. Still reflects light and able to show shadows.
Okay. Did anybody not decide it was no longer paper when they tore it down? Yeah. Can you please comment on why?
I just felt like it's so small and it's not really, it's more like a little paper thing, like dust almost.
So you've progressed from a piece of paper to something that makes up the piece of paper. You've gone to like another stage. Okay.
And I think if I take it wood, I don't know, if I take a table and I like sand it down, then don't I just get sand? Like, it's not paper.
That's a great question. So if you take a table, let's not do that here because I get in trouble. I just take some sandpaper, I get some sawdust. Is the sawdust table? What's changed about it? Structure. Doesn't look like a table anymore. What else? Yeah.
Doesn't have the same function.
It lost its function. You can't put anything on sawdust and that didn't stay there very long. Anything else? Difference between sawdust and table. All right, so structure and function were 2 main things. So when you got your piece of sub-paper down into something, did it have the same structure? What do you think? Yeah. Tell me why.
Well, you said as small as we could rip it. I couldn't rip it very small, but it was still flat. It was still like solid and
Mhm.
you know it had the same properties of paper, just flat and solid structure.
Okay. And you mentioned that you believed it was still made out of wood, so the composition was the same. Any other comments on structure? What about function? Does it still have the same function?
I was actually trying to redo with my pen, and I definitely took the right on it.
Okay.
I mean, it technically still is able to be written on, just not very much.
Okay. All right. It tested the function. I like that. All right. So, you know, this exercise is sort of meant to explore what we consider fundamental properties of matter, right? So when most of you concluded, not everyone, most of you concluded that when you tore this down to the very, very smallest part you can make, it still was basically paper. And it wasn't the same shape and wasn't the same size. So these are probably not the fundamental characteristics of what makes paper, because you can change those things, right? We can have different sheets of paper all over the place here. But there are some aspects like structure, what the stuff is actually made out of, what its physical properties are, at least in terms of, you know, if you want to set it on fire, don't do that. And whether it actually does the thing it's supposed to do, which is able to hold writing, are all sort of these test fundamental properties. And so, you know, this kind of same inquiry is exactly what sort of proto-chemists were doing for hundreds of years, starting in sort of the 13th, 14th century, of trying to see what is actually this thing made out of, right? Again, matter being this sort of mysterious substance, if we want to get down to what the core properties are, we have to decide of what happens if I tear this or change this or melt this or burn this. At what point do I have a different substance? And what does that relate to the basic fundamental substances? So I'm going to jump ahead to the 20th century and sort of give you the sort of hierarchy that we have today about what the sort of structure of matter is. You guys are working right here and basically couldn't get yourselves any further past this because the tools we have with our fingers or just simple little pens and stuff like that really don't allow us to sort of jump and scale to smaller pieces. But if we were able to do that, if we had the tools to do that, of course, we would find that compounds are made out of molecules are made out of elements, and I put down here sort of like how many of these things there are in the universe. I don't think we could really count molecules and compounds. We probably could count molecules to some degree, but of course, you can always make them infinitely complex, particularly when we talk about organic molecules. So maybe there are just too many to count. But of course, as we get further down, the complexity and all the stuff that we see in this room starts to get simpler. There's only about 118 elements that we know about. In fact, many of these elements are not things that we find in nature. They're things that we make ourselves in nuclear reactors. And of course, we can go further from there. So this is sort of the scale of the atomic. We can go down to the substructure of the atom. And of course, you should know that the atom is made out of nucleons and electrons. So nucleons are sort of the next step down. These are protons and neutrons. And even those things are made up of particles themselves. The protons and neutrons are actually, in fact, made out of these other subatomic particles called quarks. And it's the quarks and what we call leptons, but just think of an electron as one of these leptons. These are sort of the very fundamental, most fundamental particles that we know about in nature. They're the things that if I tear and tear and tear and tear and tear, I can no longer tear anymore. Now, it was actually the ancient Greeks that first thought of this idea that there was a fundamental limit to how much you could tear things down. And that idea got lost for many, many years. But now we do know from measurements that there are sort of these baseline sort of fundamental pieces of nature that then when you put them together make essentially everything that we see. Now, there's a couple caveats here. I made a couple of, so there's this gray line here that quarks don't just make nucleons, they make other kinds of particles called mesons. We are totally not going to talk about that, but if you're a physicist, this is something that's interesting for particle physicists. All of this matter also has its antimatter counterparts. So there are things like anti-electrons, anti-protons, and you can make those into anti-hydrogen atoms. Very rare substances in the universe because once they meet with other matter, they completely destroy each other. And for some reason, our universe is made out of one flavor and not the other, or at least this part of our universe. Right? So there's a whole other universe of other stuff here. And I mentioned on Thursday that there's also this other mysterious sort of substance that interacts with gravitational force called dark matter. We have no idea what it is. It doesn't fit into this hierarchy. And there's a lot more of this than there is this regular matter. Again, something we're not going to talk too much about in this class because as far as we know, we don't know of any life forms made out of dark matter. However, if it's 8 times as much of the stuff as matter, you know, Maybe there's lots of dark matter left. We don't know. But we don't know what it is, so we're not going to worry about it. So this is sort of the hierarchy of normal matter that we'll be talking about in class today. Now on this side, I've put energy scales, and I'll talk about that in just a moment. But so we've been playing with compounds. We can start diving down and sort of exploring some of these other aspects. And of course, those compounds are made out of molecules, and molecules you've known at least from your basic physics or chemistry biology classes are made of strings of elements that are bound together by these electronic bonds, these molecular bonds. Those bonds are from one of those four fundamental forces, the electrostatic force. This is the force that sort of governs interatomic relationships, right? The bonds that are created by either sharing electrons or sort of electrons being sort of shifted a little bit, so there's a net charge between two different ions. That will create an electrostatic bond as well. There's many different ways for solids to bond with each other, but they're all based around the electrostatic force. And the energy contained in these bonds is what we really refer to as chemical energy or chemical potential energy. By breaking these bonds, we release energy. By putting elements into these molecules, we store some of that energy in these bonds. And this is kind of the size scale. So we talked on Thursday about sort of the very large size scale, going out to 10 to the 24 meters in terms of sizes of the universe. We are now going into the very small scale where we're on the other end of this. So the typical scale length between atoms is something like 10 to the minus 10 meters, right? So for every meter in space, you can put 10 billion of these bonds together, and that would just equal 1 meter. Bonds are tiny, tiny, tiny things. We're going to get back to this molecule in a little bit. Now, those bonds not only create sort of combinations of elements that match together, but they can also give rise to different forms of matter, right? We'll be talking about a lot about these, particularly when we talk about planet formation and what kind of substances are particularly useful for life. But you should, of course, know that there are sort of three main ones that we see in our interaction in everyday life: solid, liquids, and gases. Water is a really interesting one because we see all three of those forms sometimes in the same case. This picture right here of a glacier in the ocean with the air above it, there's water in both solid, liquid, and gas forms at the same time in this one image. So substances can exist in multiple forms simultaneously in some environments if they're around a particular transition. But all of these are based on the sort of strength of the intermolecular bonds that are linking those molecules together, right? And this is sort of at the level of substances, right? Hard table, heated up, it's going to be a liquid table. Now, this is probably one that you're not as familiar with, but this is actually the most common form of matter in the universe, this plasma. This is what happens when you take molecules, you heat them up till you're down to the individual atoms, and you heat them up even more, you strip off the electrons from those atoms. That's a plasma form. Those are charged particles that are sort of in a soup together, and most of the universe is in a plasma form. Most of the gas between the stars, most of the gas in the stars is in this plasma form. We're not accustomed to it because it requires very high temperatures, and here on Earth we don't have as high temperatures, which is good for us, right? Otherwise we wouldn't have bodies. We'd be plasma, right? Maybe we'd plasma life, I don't know. We'll see. And of course, just like energy, you can transfer between these different phases, and so we have all sorts of different words between transferring these. I'm not going to spend too much time on this, but I just keep in mind that we'll be using some of these words off and on. So if you're unfamiliar with things like dissociation or sublimation, please take a look at the vocabulary. And in order to sort of assess what phase things in, we have these diagrams that plot pressure versus temperature for different substances. So you'll be seeing these later on. This is the case. I think this is for water. Yeah, it's 0 degrees, 1 degree. So this is a map between pressure and temperature that shows you what kind of state the substance might be in this case, water. And you can see that in general, if you have low pressures and if you have high temperatures, you're usually in a gas state. That kind of makes sense, right? If you boil water, you get into a gas state. Low temperatures, any pressure would be solid, and then this kind of magic regime in the middle, where you have the substance that's between solid and gas, which is this liquid. Liquid water is extremely important for us, and so that's one of the regions we'll focus a lot when we talk about what qualities of a planet are particularly useful for life. All right, now, so that's sort of a general property of substances down to molecules, but how do we go further than that? Well, I'm going to try a little experiment here. So again, in the sort of 15th, 16th, 17th centuries, scientists were interested in knowing what the basic components of matter was. And they did it by performing the sort of first rudimentary chemical reactions on substances to try to purify them, to try to find out how do we break these down so that we can get the most common substances. So I'm sure most of you had done this at some point. Yummy. And made a nice marshmallow molecule. The amazing thing about marshmallows and sugar in general is that when you break the bonds, you create a self-sustaining reaction for a little bit, not too pure. Because the energy contained in those bonds is enough to keep the reaction going. This is an example of an exothermic reaction, right? As we're breaking down the bonds of sugar by essentially just adding oxygen. All I've really done is sort of added a little kit to start this reaction, but all it is it's a combustion reaction. I'm just adding oxygen to this. The release of energy from that, both carbon dioxide and water, produces enough energy where you get a nice dark shell around, and I can take it off and start all over again. Yum, yum, yum. Now, what is this dark shell? What's that? Burnt marshmallow. What's its main composition? Has anyone seen?
Carbon.
Carbon. This is what burn stuff looks like, right? And when we burn organic substances, if we burn our hot dogs, if we burn, wood or something like that, we get this residue of carbon. I don't have this on the outer part because this is for complete combustion of glucose. But in fact, if you look at the ingredients for marshmallows, it's not just glucose, it's all sorts of stuff like cornstarch and stuff like that. Long chains of carbon, you're left with a lot of extra carbon left over once you break away these oxygen-hydrogen bonds. This stuff we couldn't see. We couldn't see the outputs of this because that's just a gas. It just floated away. Excuse me, we can further break down some of these things. So I've taken a complex substance, a sugar, broken it down into much simpler substances, things that are just made out of three elements, right? Very small molecules. I can go even further with this. So another common reaction that we'll talk about, actually mostly when we're talking about how we get off the planet, is electrolysis, the reaction between hydrogen, oxygen, and water. In this case, so this was an example of exothermic reaction. If we want to take water and simplify it even further, this is an example of an endothermic reaction. We have to add energy to it to make it go completely. So imagine I collected some water from this and I put it in this cup. Wow, amazing. In order to sort of actually split up this water, I need to add energy. And I'm going to add energy by adding a 9-volt battery, right? And I'm going to pass around a couple of these. What I want you to see is as I don't know if you can see that from where you're sitting, but as I add this, I can actually start decomposing the water in the glass just by adding a little energy to it. So I'm going to pass this around for you. And just experiment with putting the two ends on the metal plates in the bottom and seeing what you see. What you should be seeing is, wow, that's really sticky. What you should be seeing is actually bubbling up of these much more basic elements as I break down the water, right? And one side you're getting hydrogen out of it, one side you're getting oxygen. Most of the time you're just going to see the oxygen because that makes kind of the bigger bubbles. An experiment with flipping the battery around, you can see that it actually changes as you go back and forth. So through all of these kind of chemical reactions, and this is just an example of two, which we'll visit again in this course, you can see that it's possible to sort of purify, refine complex substances that we see in the world to more basic substances. And at some point we get to substances here where I could certainly dissociate these gas molecules. Instead of having H2, I could have two H's at high enough temperature. But I can't change the substance anymore. We've reached the sort of most basic substance. And again, much of the early forms of chemistry is developing processes where you can get to these most basic forms and discover these fundamental elements in our universe. So once this list of stuff was grown, and of course, there are some elements you just knew about because they just lie around on the ground, like gold and silver, that don't react very strongly, so you can just pick it up and there it is. Early scientists began to sort of organize these things, and particularly in the 19th century. This is an image from one of Mendeleev's 1869 papers where he starts to develop this sort of idea of the patterns of the basic elements. So once you can isolate these substances, you can look at how they react with other things and what patterns you start to see. And indeed, you start to see patterns that develop in terms of, everything, for example, in this row, reacts with hydrogen in very similar ways, right? They bond very strongly with hydrogen. Everything in this row appears to be a metal of some kind, right? It conducts electricity, it's luminescent, it's shiny, right? It has particular properties for thermal conductivity. These patterns start to emerge. And so even though we've taken this essentially infinite pile of stuff that's out here in the universe and condensed it down to, in this case, something like 60 or 70 individual elements, even those start to show patterns, right? So there must be something more fundamental underneath them. And of course, we know that that fundamental pattern is just the structure of the atoms within them. Going back down to the scale, so all those elements, all those molecules are composed of atoms, and those have two different parts, the nucleus and the electrons around those nuclei. A nice neutral atom, which is something that we see here in our sort of normal environment because we live in a pretty low temperature environment. It's going to have just as many electrons as protons. And this is a structure that we've discovered, but again, it came about because of noticing the patterns in these, what we thought were basic things, elements. We now see that there's more basic structure beneath it, more patterns underneath it. Just for scale, these are the kind of sizes that we're talking about. I mentioned this 10 to the minus 10 meters as being the length scale between molecule bonds. It's actually due to the size of the atoms themselves, and more actually the clouds of electrons that surround these atoms. Again, about 10 to the minus 10 meters. To probe down to the small thing in the middle there, we actually have to go now 5 more orders of magnitude in size. When we did the sort of order of magnitude walk out into the universe, do you remember there being big jumps in scale? What was sort of the typical size scale of, say, between two different stars? What unit was that? Light year, right? The nearest star is about 4 light years. So light year is a good typical size for distance between stars. Now, does anybody remember what the distances between galaxies is? Hazard a guess? 100,000. Any other guesses?
100 million.
100 million. How many? 4 million? So order of million? Billion. All right. So the nearest, actually, the very closest galaxies of the Milky Way are the Magellanic Clouds. They're about 50,000 light years. 50,000 light years. So it's pretty close to your scale. The nearest large galaxy is about 4 million or 2.5 million light years, which is Andromeda Galaxy. So that's about million light scale. So somewhere in that 100,000 to million light year scale is the distance between galaxies. That's 5 orders, 6 orders of magnitude higher. So there are these jumps in scale in our universe, and we see them not just going up, but we see them going down. So while the electrons fill up this sort of sphere about 10 to the minus 10, the thing in the middle is 5 orders of magnitude smaller than that, right? Tiny, tiny, tiny. Now, how do we know this? Well, there was a classic experiment that a few German scientists did back in 1911, where they shot alpha particles, which we'll talk about a little bit, are just the nuclei of helium atoms, the very, very small nuclei of these heliums, again, very tiny things. And they shot it at a piece of gold, and at the time, the model of the atom was just sort of, some kind of sphere of stuff that's 10 to the minus 10 meters in size and just kind of uniformly distributed. And so these tiny little nuclei should just go right through and pass right through and nothing should happen. And in fact, most of them did, but a few of the particles bounced off like they were bouncing off solid walls. The way that Rutherford actually described this experiment many, many years later was that it was like taking a bullet and shooting it at a tissue paper and having it come back at you. Right? How do these really fast high-energy particles suddenly bounce off something that should be basically transparent, all right, completely transparent? And the only way that was to get very small reactions and very strong ones is to have an ultra-dense, tiny little part in the middle that only a very small fraction of these alpha particles can interact with. So this is the classic experiment sort of describe what the structure of the atom looks like. The main point is to think again about this sort of jumps in scales, right? There's a big cloud, there's a tiny nucleus. We're getting smaller and smaller as we go further down. Now, just some terminology to keep us on track. When we talk about these different atoms, we are really counting the nucleons inside of them. The nucleons, again, are either protons or neutrons. The atomic number, or which really describes the element, is the number of protons. Again, if you have a neutral element, no net charge of 0, you have to have just as many protons as electrons. So that also describes the number of electrons. The other number is the atomic mass number. That's the total number of nucleons inside the atom. The nucleus is actually the thing that determines the mass of the entire atom. The electrons are tiny in comparison. They really don't contribute any matter to the matter of the atom. It's all in the nucleus. So if we want to figure out the mass of elements, what we're really doing is counting the number of nucleons in each of their nuclei. So those are two numbers to count those. And then when you rank all these out, put these all in a line, add them up by the number of atomic number, right? So we're going 1, 2, 3, 4, 5, 6 across here. We could just draw a line just like that. But if we go back and look at the chemical properties, this is the pattern that emerges, our modern periodic table, the sort of extension of what Mendeleev was doing in the 19th century. And it is a progressive table. You are stepping up to higher atomic numbers, more protons inside there, more mass as you go further along the table. But there's also these other properties that seem to have patterns that are very weird patterns, right? A pattern you'd like to think of as just like a circle or a square. This is like a weird shape. So there's something, again, about this pattern that tells us something about the structure of the atom itself. And if you've been paying attention in your chemistry class in high school, you know that that's because it depends where the electrons actually sit around the atom. That there are patterns to where the electrons are allowed to be at given distances from the protons. You have sort of these inner shells that are allowed to have 2, outer shells that are allowed to have 8, next outer shells are allowed to have 18. If we go back to this number, we see 2, we see 8, we see 18. We add in these more, we get sort of the next step. So these numbers are telling us something about the fundamental structure of the atom itself. And of course, now we understand that structure because of quantum mechanics, really just in the last century. But the patterns were already there when we were starting to just look at the chemical properties of the elements. So the one thing I want, so in addition to sort of understanding sort of this hierarchy and this basic structure of matter and of atoms, which hopefully you've seen sometime in the past already, I want you to kind of reflect on the sort of process, looking for patterns and seeing what underlying structure is giving rise to those patterns. That's how we sort of dive into the sort of core of physics. Okay, let's get through it here. So how do we build these things up? Well, if the different kinds of atoms are just, I start with 1 proton, I add another proton, a couple neutrons, I get helium, I add another proton, another neutron, I get lithium. It's just adding up these nucleons and making them bigger and bigger. It seems like the process of building them is just adding more nucleons together, right? And indeed, that's the case. That's fusion. Now, there's one problem, though, is that I sort of briefly mentioned in passing that those protons are positively charged. And there's a fundamental force of nature in which 2 charges which are alike repel each other very strongly. What force is that?
Electrostatic.
Electrostatic. It's written on there, yeah. Right. So the electrostatic force does not like having like-charged things being close to each other. It forces those apart as much as it can. The atoms are fine because what you're talking about is positive nuclei and negative electrons. They like each other. They stay together. In fact, one of the problems of quantum mechanics was solving why didn't they just merge together and just make one tight little blob. And that, again, has to do with the quantum mechanical properties of electrons. But making atoms bigger, more massive, all these different elements is another problem entirely because electrostatic force just keeps pushing things apart. You can't get past it. Right? So that's where the sort of the identity of another force, another fundamental force of nature had to come into play. And it was not something that just automatically, oh, of course, we just need this other force. A lot of people wanted to modify electrostatic force, figure out different ways of writing it down that maybe allows this kind of thing. But in the end, it really comes to that there's another force of nature that acts at very short distances and bonds these nucleons together so strongly that electrostatic force is basically useless at that stage. And that's called, such a strong force is called, of course, strong force. Very creatively said. All right. So in order to build up the element, the periodic table, you have to have this short-range strong force. It is something like 10 to the 5 times stronger than the electrostatic forces that we're taught, 10,000 times. Here's another big jump in scale, 10,000 times stronger, which means these atoms are really strongly bound, right? They're not going anywhere. However, in order to get these two things close enough together, you actually have to get past some of that electrostatic repulsion, which means you got to put a lot of force, a lot of pressure, and you've got to have a lot of this stuff very close to each other before you can get this fusion to occur. And so the sites where this fusion occurs is mostly in the universe inside stars, right? Inside stars where you have an extremely hot core, right? In our sun, for example, is about 15 million degrees Kelvin. You also have an extremely dense environment, right? Many, many, many orders of magnitude denser than, you know, the air in this room or the wood on this table, and even substances that we can deal with normally here on Earth. Extremely dense, extremely hot. Those are the sites of nuclear fusion, and that's where elements are made. They get made in chain reactions. So for example, in order to get from hydrogen to helium, from the lightest element to the next lightest element, there's a series of reactions that take protons, merge them together, occasionally once in a while flip one of those protons into a neutron, and that's where our weak force comes into play, this sort of transforming force that allows some of these nucleons to transform into each other. But over time, over sort of this whole scale, what you end up with is, starting from 4 hydrogens, you end up with 2 hydrogens, helium nucleus, and a bunch of other stuff that sort of flies off, and some energy. This process of building up elements, at least from light elements to heavy elements, is a net energy gaining process. And this is why stars actually do it. And why does this release energy? Because remember that we had all these different forms of energy. One of those forms of energy is the energy contained in mass. And what happens is that when you look at the sort of masses of hydrogen nuclei, for example, you compare them to the masses of helium nuclei, or in this case, I'm comparing a proton and neutron, and when that merges, it forms something called a deuteron, right? Which is really just a proton and neutron stuck together. The amazing thing is that the process of sticking together, you end up with something that actually has less mass. This is written in mc squared. It's written in these units of electron volts, which we'll talk about in just a moment. This is smaller than what you started off with. For some reason, just sticking these things together, you lose something. Where did it go? Well, it went into actually binding these two nucleons together. It went into that strong force. That sort of 10 to the 5, 10 to the 4 times stronger force is the bonding energy of nucleons in atoms. Now, I didn't talk about the mass scale, the energy scale from before for chemical reaction, chemical bonds, when you have atoms together, molecules. Turns out that energy scale is something like 10 to the 4 times less than this. So chemical bonds are pretty weak energy container systems. They're fine for life. We don't need a lot, right? But when we're talking about scales of atoms, this is much, much higher, right? This is millions of electron volts, whereas the chemical bonds are more like electron volts. So much, much bigger. All right, so, and again, because this is larger than this, energy has to be conserved. If you lose mass energy, the energy has to go somewhere else. And the energy goes into essentially radiation and heat. And that's what keeps the sun from collapsing on itself. All the thermal pressure from these reactions happening in the core. That's why suns do these element conversions. And again, that's an exothermic reaction. Produces energy, just like burning the marshmallow. All right, so that's great. So that means we can just start at hydrogen and start just making stuff and gaining more energy. And this is what happens through most of the periodic table. As you fuse these nucleons together at high enough temperatures, you increasingly get to more complex, more massive elements. And you're continually releasing energy in the process. The bonding energy gets stronger and stronger. But it hits a limit. And that limit is somewhere around iron or nickel. And beyond that point, you actually lose a little bit of energy every time you try to stick a nucleon. And this has to do with the balance between that. Remember I mentioned that there's a strong force that bonds these nucleons together. There's an electrostatic force that tries to push them apart. As you build these atoms bigger and bigger, you're actually building the size of the atom bigger and bigger. Right? So here's a really big atom, lots of protons and neutrons. The size of this is really just kind of the close packing of little spheres. Which goes as sort of the number of nucleons to the 1/3 power, all right? That's just a volume law. And at some point, the radius over which this is covering is starting to get beyond that short-range strong force. I mentioned briefly that strong force is a short-range force. it really only acts over the scale of something like 10 to the minus 15 meters, which not incidentally is the size of nuclei. And it's not incidentally, that's what sets the size of nuclei. Once you start making those nuclei too big, that strong force can't hold them in anymore. It's too short range. And so not only do you get to the point where you don't actually get much energy out of adding nucleons, you start to get atoms that just fall apart. And so at very, very massive, very high atomic numbers, right over here where you've got uranium, radium, actually I labeled ones that are radioactive. These elements like to fall apart because that strong force simply cannot reach the entire nucleus and keep it together. So nature has set up sort of a limit to how many elements that we're allowed to have because of this balance between where the strong force can act and this, again, repulsive force of electrostatics that's always there. Pattern of nature doesn't have to be that way. Strong force could act over twice the distance. You'd have, 8 times as many elements in our periodic table. But for whatever reason, our universe is set up so that we have a limit to where those elements can actually be. Okay. All right, any questions on this? I'm going through a lot of physics pretty quickly. So if there's any questions, any confusing points. Crystal clear. Okay, all right. All right, so I'll just describe the process of making these elements, right, out of the sphere fusion process. I haven't quite made the full closure because, these things are made inside the centers of stars, but they're also inside us. And we are not in the centers of stars. I don't know if you've noticed. So and one thing I mentioned very quickly in the last class, the universe starts with very basic elements, hydrogen, helium, a little bit of lithium. We're made out of much more complex elements, carbon, nitrogen, oxygen, phosphorus, sulfur, right? How did that stuff get from the centers of stars out to us? Well, that has to do with the ends of star lives. Many of the heavy elements themselves are created when stars blow up at the very ends of their lifetimes. And many elements that are created as the star is evolving, just fusing from hydrogen to helium to carbon, are released into the universe from these kind of explosions as well. So when we talk about supernovae at, was it 9 billion years ago? Those supernovae are critical because those are the things that get the elements out of stars, and in some cases actually make the elements that eventually end up on planets and eventually end up in us. So that's a pretty key part of this process. So going back and looking at the periodic table, so hydrogen, again, helium, and a little bit of lithium are things that are made very early on in the universe. Everything up to about iron are things that are made in the centers of stars. And I should be very clear, in fact, our star is currently only making helium. Many of these other elements are made out of very massive stars. Stars much more massive than the sun, and actually much more rare than the sun. But that's where you have enough energy, enough heat to actually create these high elements. And then those that get out, and all of these get made in the sort of end states of stars when stars die. We're going to go a little bit more in sort of stellar evolution when we get to that point in the course, but I want to sort of connect this back at least to where the elements come from and where our elements come from. I mentioned carbon, oxygen, phosphorus, sulfur, right? All these things are things made in stars, but they have to end out of stars in order to end up in us. Yes, ma'am.
I've heard that a lot of gold is actually made in neutron star mergers. Is that true?
I have no idea. That's the first time I've heard it, but I'd be curious to find out.
Okay.
Yeah, so I mean, some of these are pretty, so reasons that we think that these are made in stellar explosions because you need a hell of a lot of energy to make this stuff. You're not gaining energy by making these elements, so you just got to have a lot of excess around that you're just willing to burn. And a supernova produces a tremendous amount. This is the star completely blowing up. And it's that excess energy that allows these other elements to get made. Essentially, you're taking all the excess energy and you're putting it into potential atomic energy, the potential energy of the nucleus itself. Now, what happens to that energy? Well, actually, those elements start to fall apart, as I mentioned, right? Big elements, really massive elements like uranium, radium, fall apart. In the process of falling apart, they actually also release energy. Because it's more energetically favorable, there's less mass to get the smaller particles than the big particles. You get the opposite of what happens with fusion. And it turns out that this is the main power source for the Earth. The center of the Earth, I got the temperature right here, the center of the Earth is something like 6,000 Kelvin, not 15 million Kelvin. You can never do fusion at these kind of temperatures. We're trying, right? We're trying to do fusion here on Earth. You definitely can't do it at 6,000 Kelvin. So something else is keeping heat going inside the Earth, and it turns out that that heat is mostly from the decay, the fission decay of heavy elements that were made in supernova explosions in the past. So there's two heating processes that are related to elements, fusion and fission. Fusion is happening inside stars, producing energy. Fission is happening inside planets and also producing energy. Both of these things are very important in sort of understanding how planets and stars work. Okay, so I'm going to just finish up. I think I have one more slide here. So one more step down, like a couple more slides here. So one more step down is looking at the nucleons, the structure of the nucleons themselves. And I'll just state that we know that the nucleons are made out of these more fundamental particles called quarks. They come in different flavors, up, down, strange, charms, top, bottom. You've probably heard some of these names before. They're, again, held together by the strong force. And at least in terms of nucleons, they always come in triplets. All right, up, down, down is protons and neutrons. And those combinations of quarks actually give rise to the charges that we have for these nucleons. Now, one last reflection. So I talked about sort of the different energy scales. Why didn't Newton know this? Why didn't Newton know this? That's a tough one to say. Why didn't Newton know this? Why didn't he know that matter is made out of atoms, and atoms are made out of neutrons and protons and electrons, and that neutrons and protons are made out of quarks? Why didn't he know that? Why didn't everyone know that? Why do we just know that now? So technology is part of it. Remember, we were cutting the paper. Some of you actually used your pens, or you, I don't know, fingernails. You haven't cut for a while. You had tools to break these down. That's part of it. It's having the right tools. Another aspect of it is having the right amount of energy. So we go back and review these energy scales. The natural sort of unit for energy at the sort of atomic molecular level is something called the electron volt. It's really the energy that you gain by taking an electron and moving it through 1 volt of potential. You've got batteries out there that are 9 volts. So if you take an electron and put through a 9 volt potential, you've got 9 electron volts of energy. Right? That's all. It's very easy. On the scale of molecular bonds, the energy contained in those bonds is something like 1/10 to 1 electron volt. That's the kind of energy you need to break up those bonds. Or it's the energy you get out from breaking those bonds up. Right? And that can be done in temperatures that are pretty typical here on Earth, hundreds to thousands of Kelvin. Right? You can boil, complex sugars and break them down just in a pot or with fire. If you want to break apart the atoms into their constituent parts, the nuclei and the electrons, you've got to go up an energy scale. You've got to have enough energy to actually rip that electron away from the atom. And that takes it actually more of on the sort of next order up, 1 to 10 electron volts. In fact, even in some cases, a little bit more. Right? That's how we go from normal sort of gas, solid, liquid matter to plasma. And those temperatures are much higher, thousands and tens of thousands of Kelvin. That's why we don't see plasmas around that often. It takes more energy to break those apart. If we're going up to the next scales, again, we're jumping up to higher temperatures. Breaking up nuclei is on the order of thousands to millions of electron volts. Incredibly high temperatures. These are the temperatures that you need inside stars in order to make this happen. Right? That's why we don't see fusion happening very often here. It's actually good, because if fusion was much easier to do, everything would fuse together, and then we wouldn't have hydrogen and stuff like that to make hamburgers. And if we want to go even further in scale and understand the fundamental properties of the nucleons themselves, you're breaking up the actual rest mass energy of nucleons, and that's now into the billions of electron volts. So Newton didn't know this stuff because he did not have anywhere near that kind of energy available to him. But for example, the CERN experiment in Geneva can go up to 3 orders of magnitude higher than this. So it's really the development of really high energy tools, access to higher energies, access to sort of more, sharper knives, you can think about it, or high energy knives. It's the only way that we've been able to break up these different things and see the fundamental properties. But in all cases, you can still discern the patterns. Okay, any questions on that stuff? Okay, so Thursday we'll be talking about light. I've got 1 person signed up for news. I'm taking down the link for the news sign up today, so make sure you put in your requested time or I will start assigning. Yes, ma'am.
Are you gonna go for the schedule?
Yeah, I'm putting them up on the Google Calendar as I get them. I'm probably like a few days behind. So I will have that set up. And I will notify you of your time before your time. Okay. See you guys Thursday. Oh, actually, yeah, see you guys Thursday.